Hello, and welcome to the HaS2 Aerospace Village demo. HaS2 is a computer security competition focused on topics and skills useful to those working in the space domain. During the final event of last year's competition, Cromulence developed and built 16 model small satellites for the 8 teams that qualified. These flat sats were used as the target systems the competitors needed to hack into during the event. In support of events like this, as well as our other customers, Cromulence prefers to create system models with full system emulation, running the real software from the system on emulated hardware. This is why we designed a digital twin of our flat sat from last year's finals. A digital twin is simply a virtualized model of a physical device, in this case the various CPUs and sensors that make up the real physical hardware version of the flat sat and flat sat ground control system. The individual emulated components communicate and interact such that they match the real-world system components. For space systems in particular, this is a powerful tool that can aid both development, operations, and security. This is our FlatSat's digital twin. This is a virtualized version of the updated FlatSat we developed over the last year. The version you are seeing today was developed for another event Cromulence supported earlier this year. At its core, the digital twin is built on top of Cromulence's custom emulation platform, HaG, which is itself built on top of the open source QEMU project. This emulation platform allows the digital twin to emulate the real FlatSat hardware at the instruction and peripheral level. The 2 digital twin HaG instances are used to emulate both the Attitude Determination and Control System, ADCS, and the Command and Data Handling, CNDH. This allows the digital twin to run the exact same firmware and software binaries as the physical hardware FlatSat. There is no need to recompile a different version or change configuration in the ADCS or CNDH flight software when run with the digital twin. There are many inner working components within a real spacecraft, including both communication between processors and between peripherals. The easiest way we were able to virtualize a satellite was by utilizing HaG. Our HaG emulation framework allows us to develop emulation plugins in both Python and in C that run alongside emulation. These plugins can range from creating new emulated devices and their communications to analyzing virtual and physical memory of emulations on the fly, which allows for powerful introspection on emulated systems. For the digital twin, we use this plugin system to provide simulated truth data to the emulations through the various protocols that the ADCS and CNDH firmwares are expecting. This means that there is no custom firmware built for use only on the digital twin. Any firmware that can be flashed on the actual hardware can be loaded into the digital twin with no modifications. So in short, we have flight firmware running in emulated hardware thinking it's in space. You can command it like it's a real satellite and it behaves almost identical to its real-world counterpart. So let's walk through some of the windows. On the top left window, we have our output from 42 simulation. The top, middle, and right windows are running the IMU and wheel plugins. These take the values from 42 and communicate them to the ADCS emulation through various serial protocols. The bottom left window contains our CNDH firmware, which is currently running on a Spark emulation. And the bottom right window contains our ADCS firmware, which is also running in emulation. Now let's move to the ground station and command the satellite. We can command the digital twin just like we normally command the FlatSat. We're also receiving the same telemetry that we'd receive with the FlatSat. These packets are sent over an emulated network to a simulated radio which Cosmos then communicates with. The first thing I'm going to do is enable telemetry by sending the emulated CNDH and enable telemetry command. Once I send this command, we should start seeing packets coming in. Next, we can command the digital twin to spin its reaction wheel. Once we send this command, we should be able to see the digital twin slowly start to spin in the visualization within 42. Let's bring the speed up a little bit. Let's set the RPM to 500 and send the command, and we should see the satellite spinning a lot faster than it was before. And there you go. You can see the satellite in the visualization is spinning much faster than it was at 100 RPM. Now let's change it to the sun yaw control mode. This will allow us to specify sun yaw angle we'd like the satellite to point to, and our sun pointing algorithm should do the rest.